It's a little bit past time, but that's all right. We're hanging out. Couple random announcements. If you've heard us talking about the CDC up here for a while, don't sign up now. I guess that's not okay. And they, instead of preventing you from signing up, they just expect you not to, with no indication of why to or to not. So don't sign up for the CDCs yet, or I guess your accounts will just be wiped tomorrow.
I don't know. We weren't aware that sign up was even working at the moment.
Okay. So just don't sign up. We'll sign up tomorrow, I think. Yes.
The thing that was put out in group chat earlier today on Discord.
About what?
Is that it was like some kind of like Ctf related thing?
Oh, that was a different thing I want to talk about. I'm going to talk about this as well. I think if this is what you're referring to. So first off, CDC stuff, that should be, if you're in 230 or 331, I think Julie threw some stuff in some Slacks, but the cyber defense competition, our first one of the year, will be hopefully kicking off tomorrow in terms of you can sign up, you can get access to the scenario, and you can start looking at machines, which are like the three most important things. So if that does happen, like I've been told it would by Doug and Julie, then we will throw something in the Discord with more information about how to sign up and that sort of stuff. And then also, for anybody that was looking up here when we were just talking around, our tentative plans for the rest of the semester's meetings, we've now penciled in CDC kickoff for next week. So next Thursday's meeting will most likely, unless there's like some catastrophe with Ice Age, which we're not ruling out, will most likely be a kickoff event where you can come, and it'll be, we'll try to be a one-stop shop for information about it, how to form teams. We'll help you guys get set up into teams, because I know there's a lot of people who have never done a CDC before and need to find a team of other people who have never done it before and are okay with learning. So we'll help set up teams. We'll talk about what all you need to do and some of the tips and tricks we've used to be successful in the past, or our team specifically. So there's that. That was the first little announcement. The second announcement was this big ass post that I threw in the Ctf channel for the Discord. I tagged everybody, not just Ctf people with the Ctf tag, because I think it's really important. So this is Cyber Fast Track. Hands, I know some people said this, hands if you've heard of Cyber Fast Track before. Yeah, it's also Cyber Start, or I think they had a couple different names. It's changed a lot. It's been around for a while now. So cool, almost nobody, which is why we have this. So Cyber Fast Track is, this version is it's a long-running Ctf essentially. So it goes from October 4th to April 4th, October 4th this year to April 4th of next year. It's like something, they said like over 200 challenges, 200 plus challenges, ranging from like literally everything. There's application security, there's Python programming, there's reverse engineering like we'll talk about today. Really anything you'd want to learn in the field of security, they have challenges for it. And these challenges are, like I cannot stress this enough, very beginner friendly. Like if there was any place to start learning CTFs, this would be it. This is probably where I made the most growth. I started doing this, I think my junior year of high school is when they first started doing this, and I got involved with it, and it was super fun. It's crazy cool. There's a lot of cool stuff. The first that big long October to April period is more of a testing grounds. You get to get familiar with stuff. It's a chance for you to learn at your own pace, do it as much as you want, or don't do it at all. Just poke around, whatever you want. And then also, at the end of this, I believe the way it worked last year is that there was a like weekend competition. Was it Saturday, Sunday or something, or Friday, Saturday? Yeah, I think it used to be a week-long competition. I think it's only a 2-day thing now, so it's a weekend, and it's a much more fast-paced, meant to apply the skills you've learned here to a faster, real, like 2-day CTF challenge. And that challenge is where you get to prove your own medal, 1v1 some other people, and if you get high enough on the leaderboard, you get the chance to apply for some scholarships. I know we had a lot of people talking here. They give out GFACT exam attempts, which are really nice. That's a GIAC certificate. So GIAC is like one of the biggest certificate issuers in the security field. I have a couple of GIAC certificates from a scholarship that I won from these people, and so they look really, really good on resumes. A lot of students, especially like freshmen, sophomores, don't have any of these. It's not uncommon for people to graduate with no GIAC exams. So it's a really good way to look just a cut above the rest, I suppose. So I wanted to give a quick shout out to this because this is going to be like, I would say really important. I would really, really highly encourage everybody to sign up for it, even if you don't want to compete, even if you don't think you'll have the time to do it. Just getting access to the challenges, you have a free weekend or whatever, you can poke around at a couple of them.
I would tend to say I got maybe 30% of the way through all the challenges, and I did get a free GFACT exam, so you don't have to do a ton of it either to get the free exam. You just have to be in like the top percentage, and there's a lot of people that sign up, so it's really easy to hit that top percentage.
Yeah.
Because a lot will sign up and do nothing.
Yeah.
You'll see that a lot in cyber with any CTF. There's going to be
Yeah.
a lot of people who sign up and do nothing.
And that's fine. That's cool.
Yeah,
Signups
it's
are free.
fine.
I was gonna say the exact same thing. I got like 25% of the way done, and they gave me a scholarship for it.
Yeah, no, it's crazy. I did it, so I got, like I said, I got like one of the bigger scholarships. It was like, it was a program at the Sands Technological Institute for doing an undergraduate degree with them. And I actually just finished that up over the summer. It was like 5 classes. I earned like 3 or 4 GX certs, and it was all paid for by this CTF. And that total price, if you were to pay it out of pocket, would be like 18 grand. So, you know, you can win, you do as little as you want to win a $500 scholarship or just one of these exam attempts, or you can really go balls to the wall and try to go for everything. So, yeah, wanted to throw that out there. There's a sign up link there. I think that's just to get notified when it starts starting to do intake, because they have a lot of people sign up for this every year now. So, cool. That should be everything on that. Trent's throwing a bunch of stuff. Oh, cool. We have a CDC role.
There is now a CDC role and a CDC section with channels that you can't actually view until you get the role.
Cool. So, new role in the role selections channel. I'm glad we're getting our use out of this. Wait, no.
Yes, it's that
Is
one.
that the role?
Yeah, sorry.
Okay, the chats hasn't been updated yet. But either way, grab that role if you're interested in doing the CDC. And then here's where we will post, are these the boxes?
Yeah.
Okay. This is where we'll just post general info about joining teams. Maybe we'll make a team selection channel, a whole bunch of stuff. It's super fun. Again, looks great on resumes. Highly recommend CDCs. So cool. We'll let them handle that, and we'll jump into the formal topic for today's presentation, which is throw in reverse, or just reverse engineering in general. Trying to be Zoomer friendly here with these titles. I got to get your guys' attention. So, okay, cool. So, what is reverse engineering? So who's heard of reverse engineering like in any context, whether you know anything about it or just heard people talk about it? Yeah. So like, it's a pretty common cyber field. It's the company I worked at, Mandiant, over the summer. They have I would say like a third of their team is reverse engineers. It's called the Flare team, and they have internships. If anybody wants to apply, they're super cool. So reverse engineering is the process of working backwards, generally from a compiled program. It doesn't have to be. There's a lot of different things you can reverse engineer. But the idea is that you're taking something you know nothing about and moving backwards to the building blocks of it, whether that's the code it runs on, whether that's the protocols it follows for communications or the guidelines or whatever it is. That's the overall flow of things, is we're going backwards from what somebody had created and pushed out to the public. And now we're taking that thing that they gave to the public and we're figuring out how they did it. So this begs the question, and this is a really tiered thing because there's a lot of questions here and it's a really deep topic. So that begs the question of what exactly a compiled program is. What's that mean? I understand that some people might not have the most experience with C, but C is the most common language we use here for compiling things and things that actually run in a binary format. Because most of the time when you make a Python script, Python's not going to run in a compiled format. You can export it to PyC files, I think, which are like weird compiled versions of Python, but
They're compiled for the Python virtual machine, which is technically what Python runs in.
yeah, so either way, most of this is going to be C. So a compiled program is what that beautiful screenshot on the right is. It's a bunch of garbage, usually. To humans anyway, it's a bunch of garbage. It's actually very structured and it has a very important layouts to it that compilers and computers understand as executable programs. So these compiled programs contain things like metadata about the executions, constants and strings, so things that have been stored in that program for a long time and that aren't going to change. And then most importantly, in a little section called text, it'll contain all the opcodes for that program. So when you write a beautiful C file, it's going to compile down into specific instructions for the CPU architecture that you're running on. For anybody that's taken 381 right now, that's exactly what you're going to do in 381 is make a processor and then write the actual code to run on it. As much as you hate it, it's like gave me a better understanding of CPUs than I ever had before. So yeah, the most important part of this is they have the opcodes for the instructions inside of the executable. It's just not in a pretty format for us. And so again, it's really hard to explain one of these topics without going in on another topic, so I'll briefly mention opcodes. Opcodes are short for operation codes, and they're the instructions that run on a CPU. So these are made up, but you could imagine an opcode like 0000 would be the add instruction for adding 2 registers in a CPU. 001 might be add I for add, wait, what's I? Immediate. I was like gonna say constant, but that's not it. So add immediate, which is like a constant. So, and then you could go on from there and just build out that opcode list into a full list of instructions for your CPU. And then that's how you pretty much control the program, or control how things get executed on a processor, is all these little opcodes. So recap, compiled program, bunch of binary garbage with some opcodes, which are important instructions for how the program should run on the CPU. Those opcodes can be decoded into add, I, sub, and a whole bunch of other ones. So why do we need reverse engineering? Can't we just control Z, the compiler? Like we went one way, can't we just go the other way? Like I don't know why we would need to do all this hard work. And that's a pretty common thing, but much like a hashing algorithm, it's really easy to go one way and damn near impossible to go the other way. There's information that's fundamentally lost when you compile a program. So there is information that we use to be more efficient programmers, but that you do not need. You can really go ham and just start writing in binary and nobody's gonna complain about it. But for a normal person, you're gonna write in C, you're gonna put some comments maybe if you're really dedicated. You're gonna have nice verbose variable names. They're gonna tell you everything about it. You're gonna have really broken up loops that make it so that it's like really easy to see why you're looping over or what you're iterating over. And that's all great for sharing your code and like being able to give it to other people and have them understand what it is. It's actually worthless and a waste of time for the compiler and for your CPU in general. You don't want your CPU to have to go through line by line in your program and be like, okay, is this a comment? It is, okay, throw it away. Is this a comment? It's another comment, throw it away. Oh, is this a long variable name? Let me find a place to store that variable name. That's all irrelevant for a actual program executing on a CPU. So we're throwing away variable names. We're throwing away function names. We don't need those either. We're throwing away all the comments. We're optimizing the hell out of these loops. If there are unnecessary iterations, sometimes those will get optimized out depending on what compiler you're using. There are a whole bunch of information that's just out the window when you compile it. And that's what makes it a lot harder to break up a compiled program back into the raw, actual human readable language that it was written in originally. And on top of just losing information, there's also a lot of information that is added. So, for example, anybody that, like 381, for example, if you wanted to write like a simple print statement, there's actually going to be a lot of setup for that. So if you wanted to print a string, you need to find that string and load it into memory. You need to know where that memory is located. You need to do a system call and point that system call at a point in memory to call that exact function that you want to call, which would be print, and then you need to point it at the string that it wants to print, and you need to tell it where to output it to, which would be the terminal. And so that one print instruction could one print command, depending on your CPU architecture, could easily become like 15, 20 instructions on a CPU. So that's why this binary is looking so crazy. That program that I wrote for that is not very long. It's like 5 or 10 lines for demo purposes, but it gets broken up into a ton more instructions than you would expect. So again, when you have one line broken up into 15 instructions, it can be really hard to tell what part of those 15 instructions get put back into one print statement. Because if you have like 15 instructions, how do you know that the first 5 aren't a different one line of code and then the last 10 could be one separate line of code? Where do you draw those lines? And that's all very dependent on the architecture. And when I say architecture, I'm referring to like x86 versus ARM versus MIPS, everybody's favorite CPU architecture. So, so those are all different architectures that run differently because the processor has a different set of instructions. So that's why you compile for a specific architecture, because it needs to know exactly what instructions it can and can't use with that CPU. That's why a program compiled on Parrot or Kali or whatever won't run on Windows. It doesn't have, or that operating system doesn't have the support for those instructions or those specific system calls or things like that. It's very architecture dependent. So hopefully that makes some sense as to why reverse engineering isn't as simple as just undoing the steps that a compiler took. There's a lot of information lost and added. So how do we do it? What's the process of reverse engineering? Well, it's actually really easy. So first, we'll look at the by hand method, which is personally my favorite. So first, we're going to take some raw assembly from that binary. We'll start pulling out, you can find the text section in an executable, and then it's going to be a bunch of binary hex garbage. We'll just take out one instruction from that. We'll pull out one instruction. We'll say it's that instruction. All right, so that instruction in hex there, 00101208, is converted to that in binary. Cool, we're like halfway through this battle already. We just take that binary, and then we need to find an architectural cheat sheet. Luckily, Oh my God, look, it's a MIPS green sheet for anybody who's in 381. Cool. Okay, so we'll open this in a separate tab because we're going to need that while we go along with this. So cool. So we found an architectural cheat sheet. Find one for whatever architecture you're working on, ARM or x86 or whatever else. And then here is the basic instruction format for MIPS. So essentially, there's R, I, and J instructions, and those have opcodes at the beginning, and then different fields for their registers. So now we just need to break up this long string of binary into the different fields. So here you can see that the first like 6 bits are going to be the opcode, and then the next 6 are going to be a destination register, and then a source register, and then another source register, and then a function call. So cool, we've broken that up. We've got our green sheet open. Now we just need to look up these pieces individually. So 0010, if we go back to our MIPS green sheet, we can look and find the instruction that it's running. And, well, okay, so if we're using registers, we're going to have to keep track of all the registers that we're using. So you should probably get a pretty large sheet of paper because you're going to have to start writing down what's in each register as you move it around while you're looking up on the screen sheet. Or we could just not do that. I hope the point got across there that that's going to take literally years. That was one instruction that we broke up and then tried to look up in the MIPS green sheet and everything. And MIPS is one of the simpler CPU architectures. So if you're using any modern compiled executable, by hand is not feasible. It's a fun experiment, and you'll get to do it in 381 for sure. But please don't ever try that. I don't think I could, with a good conscience, recommend anybody waste as much time as possible on that. So we're going to look at method 2, which is please don't do number 1, which is to use Ghidra or any other decompiler. Has anybody heard of Ghidra before in terms of reverse engineering? It's like the best. Has anybody heard of IDA Pro? I know that that's, or IDA, or any of the suites of IDA. Okay, so cool. Good to see IDA is still less popular than Ghidra. IDA Pro is super expensive. There's a free version of IDA, right?
Yes.
Yeah, okay. We don't talk about it. So enters Ghidra. Chomp, chomp. Let me get back into my presentation. So Ghidra has entered the chat. So Ghidra is like, it was my first reverse engineering toolkit, and it came out around when I was getting interested into this, I think. And it was amazing. It's a super automatic, super hands-off reverse engineering tool that was developed by the NSA and then released, I don't remember when it was released actually, but it was developed originally by the NSA and used in their internal tooling to try and understand malicious code better that was getting thrown around by nation-state attackers. And then they released it open source, which is pretty awesome. It handles like, and when I say all common binary formats, I mean all the common ones and then most of the weird ones. I feel like there's a lot of instances where if you're willing to put in the work and find external libraries and things for obscure compiled languages, you can even get those to work on here. So it's an amazing go-to first try if you don't know at all what you're looking at for a compiled program. And I can't say much more than it's pretty much drag and drop. We have, I've got a couple demos set up that we're going to go through basic Ghidra usage, and you guys will see how easy it is to use. Like, it really makes you feel like you're not doing anything. And then it's got a lot of really nice features. It's got global variable renaming, so if, like I said, variables are thrown out in the compilation process, the computer doesn't need those. Those are just for our convenience. So when we go back in there, we can manually rename variables inside of Ghidra, and it will carry those changes out through the entire program. So instead of just having like variable C642 or whatever, you can rename that to be like user input, and then it'll change everywhere in the program, and you don't have to remember where that variable was anymore. So it's really good at getting back to the original code and letting you choose how to do that. And then another awesome feature I've used it before is binary patching. So if you're looking into a binary and there's a comparison, for example, one way to get around a comparison is to just change the CPU instruction that's running. So instead of it doing a check for if this value is equal to this value, you could flip one bit in the middle of that binary and make it that this value is not equal to this other value. And that way you don't have to get the values correct. So Ghidra does a really good job of letting you change individual bits, and then you can save it and export it as a binary, and it's all good to go. So can't really say enough good things about Ghidra. And then, again, we'll post these slides somewhere, but I have a link to the download there.
Also, it's extensions. So if there's stuff that it can't do, you can probably find ways to get it working.
Yeah, there is a lot of third-party support for Ghidra. Like I said, it's open source, so the community is very strong around it. My company, Mandiant, actually just released a extension that allows Python 3 to work with Ghidra, so you can do a lot of interesting Python scripting inside of Ghidra if you have like really monstrous reverse engineering tasks that have a lot of repetitive behavior. So yeah, extensions are crazy awesome. It's amazing. I just threw this in here while everybody was walking in, but we're also going to talk a little bit about dynamic analysis during the demos. there's a lot of programs for this. So Ghidra is an example of a static analysis tool in which we're taking a binary that we were given, we don't know anything about it, we're decompiling it and we're reading through the code, we're understanding what it does, maybe we change a bit here or there, but in the most part it's static, not changing, and we're just absorbing as much information as possible. Whereas that's the opposite of dynamic analysis, which this is when we run an executable and we attach a debugger to it. We can pause execution. We can step executions one instruction at a time, examine register values in the CPU itself so we can see what values are being stored in the CPU. And that's a really good way to debug more complicated programs. So if a program looks like absolute garbage inside of Ghidra, Ghidra doesn't decompile it correctly, it's all spread out, there's a bunch of obfuscation. Dynamic analysis can be a great option to step through it one instruction at a time and be like, okay, here's where I can see it's reading in my user input, I'll go a little bit past that, a whole bunch of stuff. We're gonna talk about that. So there's a couple different ways to do this. Ollie debug is an older one that I don't know if is used much anymore, but I think it's mostly used for Windows executables, so that one's pretty cool. Cheat Engine, actually, James suggested that, he just left, but Cheat Engine isn't a version of dynamic analysis. It's one that allows you to attach to running processes on your computer. So it's mostly used for cheating in games. So you can attach to game binary processes and then search through their memory for your health value and then make your health value 1,000,000 because you don't care. So, because you want to see the world burn. But Cheat Engine is really cool. And then what we'll be talking about today, and my most used one, is GDB, or the GNU debugger. It's super convenient because it's installed on like every Linux distro ever. I don't know if I've ever seen a Linux distro not have GDB. And it's also just what I know the best, so we're going to talk about it. Some example commands, you can just do info functions and it'll print all the functions that have been loaded inside the program. x/x will examine memory at that location, in this case $RAX, which is register. And then disassemble just prints out the disassembled binary in front of you and you can go and look through it a little bit. So like I said, we'll talk about all of that and make a little bit of sense more, but yeah, I think we're just good to go hop into some demos. So let me hop out of Firefox here and close the cheese tier list. So first off, we're going to grab Ghidra. So Ghidra can be downloaded from GitHub. There's public releases on GitHub. All you have to do is download it, unzip it, and then inside of that folder, which is actually this folder here, there's a Ghidra run file, which you can use for this Ghidra run in the middle. The green one is used for running it on Linux. And then Ghidra run.bat is the bat file for running it on Windows. So it's cross-platform. You don't have to do any crazy compiling or any find any fancy versions of software. It just natively supports it, which is also amazing. So this is what Ghidra looks like when you first launch it. It looks pretty old school, but it's amazing. So first off, you can go new project, and you can create a new project. It's super simple. You just tell it where you want to go and the project name, and it creates it. I've already set one up here called demo. So this is our current project demo. We are going to come up to file, and import file here is where we go to grab our binary that we want to reverse engineer. So when I say that, I realize I haven't shown you any of the binaries. So I've set up a couple different examples here. Simple and less simple, and then demo 2 are all different types of reverse engineering. So let's just look at simple first for the easiest one. Enter a guess at my secret number.
17.
17, that's a great guess. I don't want to say you're bad at hacking, William, but so that was the incorrect number. Any guesses at what you guys would do if you were given a binary like this for a CTF or whatever? That's the most common example, and you had to figure out what this number was. Any commands you guys would run or anything?
420.
Strings, other than just continuing to guess. So strings, what? To guess all the numbers. You would get it pretty quickly.
Oh, it's like 2 or
What? 200 A's, that's also a good one. And that would probably break this because I wrote this C program in like a minute or so. So either way, the answer I was looking for was strings, because that's usually a really common way to get these things. So if anybody hasn't used the strings command in Linux, it will go through any binary file, or any file in general actually, and just pull out all the ASCII text. So in here we can see enter a guess at my secret number. You did it, epic elite hacking. So that's probably the answer we get if we get it correctly. And then right below that we see the incorrect guess. I don't want to say you're bad hacking, but which is what happens when we're bad. So we can see all the different parts of it, but we don't see anything that might scream or give us a hint at what the number would be, unless we were to read the text. But there's nothing obvious here that says like this is what we're looking for. And that's probably because it's a number, and numbers generally don't get stored the same way inside of a compiled program as strings do. So Either way, after we've run strings on that, we can do the next logical thing, which is to throw it into Ghidra and look at it. So Ghidra is actually going to have a field day with this one. We also have the source code here, so we could just look at the source code. But pretend we don't have the source code. So simple, we throw this in, and in our import window here, we can see that it identifies it as x64. It was compiled using GCC. It's going to throw it in the demos folder, and the project name will just be simple because that's the name of the program. And that all looks good. It also identifies an executable and linking format, ELF, which is the default when you compile with GCC. So we hit OK there. We see a dragon munching on some numbers for a sec. Here is just more information. So this is like the exif info of what you're importing to really make sure you've got the right file. We do. Cool. And now you can see it's been added to our active project. So it's just right here under demos. We can double click that, dragon pops up, gives you a bit of a jump scare, and boom, we are into this. So this is the meat of Ghidra. This is what the program looks like when it's in full operation. And the first window you'll always get is blank program has not been analyzed yet. Would you like to analyze it? And you should always say yes unless you don't want to analyze it, then say no. But that comes in here, and these are more of the crazy features you can get into with Ghidra. I'm not even going to claim to know what like 90% of these do. There's a couple that I've enabled or disabled in very specific situations, but I found that almost all the time leaving it as is good. All the ones that are unselected are usually really aggressive and should only be last ditch attempts if you can't find what you're looking for with a normal analysis. So what this, I guess just to take a step back and say what analysis is doing, this is the raw assembly. These are all the instructions that Ghidra was able to pull out of that binary, all the raw CPU instructions. However, analyzing it is where Ghidra gets really fancy and starts to do that sort of reverse work I talked about. It's going to find those groupings of 15 calls that make a print statement, and it'll give you its best guess at what the original code looked like. So we'll analyze it. In the bottom, okay, it went away so fast. In the bottom right, there'll be a little loading bar that says like what it's doing, but this is such a small program, it got through it in like half a second. So at first, it looks like nothing's changed. But if we look over here on the symbols tree, we've got imports, exports, functions, labels, classes, namespaces. First one I always go to look at is functions. And this will show you all the functions that have been defined inside of this binary. So if we look in here, there's a lot of, anything that starts with an underscore is going to be a system function. So that's one that was included because it was imported. It's needed to for certain system calls. And it's generally not what we're going to be interested in looking at. Underscore start is where the program enters at. So it's kind of its entry point into the entire program. And we can see here it calls another function called libstartMain, and that does a whole bunch of stuff. But usually what we're looking for is something with a human readable name that looks like somebody wrote it, like main. Maybe that's a function. So if we look at main here, we have an example of what Ghidra does with this assembly. So if I minimize this code here for a sec, this first part here is where Ghidra has identified a function start. So they have all functions in assembly have certain headers associated with them to know that they're functions and what their parameters are and stuff like that. So we can see here the header information for this function. And then down here, we can see all of the raw assembly. And so again, you could go through the tedious process of keeping track of all these registers and trying to understand what it's doing and comparing it to C code that you've written in the past. Or Ghidra will just do it all for you. So in the right window here, we've got the analysis and decompilation of that assembly into human readable C programming code. So I don't know if there's a good way to zoom in on this, but either way, so it's a very short program, but we can see here all of the basic stuff. So this first printf statement says printf, enter a guess at my secret number. Pretty good chance that that's exactly what we saw when we ran the program. So if we jumped back here and ran simple, we can see that that's the first line of this. So it shows we're in the right function. So it's printing out that. It then sets this local C variable equal to C, and then it calls this system function. ISOC99_scanf, which if anybody's written any C programs, scanf is like the basic way to get user input. So here we can see we're calling user input. And if anybody's familiar with the parameters for scanf, the first one is going to be the format string for how to read it in. So whether you want to read in a number or a string or one character. So we can actually double click on that and it'll take us to the reference of this data. And here we can see it's really small, but right here, it's %d. So we can tell now that this data is reading in a number. It's scanf %d. And this is where I said that renaming comes in. We can actually rename this global variable to just be %d. Hit OK, and now it's updated in our scanf function. So now whenever that comes up again, if that memory is ever accessed again, we just know it's %d right away. And then the second argument for scanf is going to be the memory address to store the data it was read in. So in this case, the second parameter is that local C variable that was set to 0 up here. So there's a pretty good chance that that's our entered guess. That's our user guess. So we can rename that variable to be user guess. And now it's starting to look a little bit more like a program. So at the top of main, we define this int called user guess. And then we print out guess my secret number. We set guess equal to 0. And then we scan in a number from the command line and store it in user guess. So then this next statement makes perfect sense. It reads just like you're programming. If user guess is equal to hex 539, then we're good. You did it. Epic elite hacking, bro. The only downside is that I don't know what hex 537 is in decimal, and we need to be entering data in decimal on the command line. So if we were to go back here and guess 539, it's still going to give us a too bad, so sad message because 539 isn't what it's looking for. It's looking for the binary or the decimal representation of that. But Ghidra doesn't care. It'll give you it all right here if you just right-click it. So there's the binary, and then the decimal, to no surprise to anybody, is 1337. So we can make it display that. And now this is back to almost, minus the scanf thing, this is almost exactly what my source code looked like for this. Ghidra was able to take that small program and translate it back almost entirely to what it originally was. So come back here, 1337, and boom, epic elite hacking, we did it. No round of applause. Usually at Black Hat and DEF CON, you get rounds of applause after cool demos. So either way, that's like a super basic showcase of what Ghidra can do for this binary. It's all kept in one program, in one function, so it's really easy to look at in one screenshot. It's awesome. I love it. Cool. So that was simple. I also had a couple other ones to show off. So if we import a file here, we can do less simple. We're going to import that, and I'm not going to analyze it just yet. So we'll look at what less simple does. So less simple is going to ask for a string now instead of a actual instead of a number. So we're not looking just for the key space for our guess here is way larger now. So it's not just numbers. We've got any sorts of letters, and if we guess it, oh, I realized I just did the lower thing, but yeah, either way. So if we enter it wrong, we get the same thing about not being good at hacking, which is annoying. So we need to figure out what the password is. In this case, I wanted to show off another technique for this. Also, side note, I'm pretty sure running strings on this works because I didn't obfuscate the string properly. There are ways to have strings stored in programs that don't show up on the strings. Actually, wait. Now I'm curious. Okay, I think it is there. So either way, there are ways to obfuscate that, and most of the time in Ctfs or in any practical scenario, that's going to be obfuscated because it's not that hard. So I wanted to use this as an opportunity to show off GDB, which is the dynamic analysis version of this. So where Ghidra will take that and convert it back into readable code, GDB, the GNU debugger, is going to attach to this program and let us view it as it runs in memory. It's not going to do any of the fancy translating back to normal C code, but it will let you see the registers that are being used and all the low-level details of the CPU as it's executing. So all you need to do to run it is GDB and then the name of your executable. Run it, and it pops up a bunch of stuff. And the important part here at the end is to say it reads in all of the symbols, and it doesn't find any debugging symbols, which is fine. This wasn't compiled for debug, and nothing really ever is. But it did read in the basic symbols for it, which means it knows where all the functions are and has guesses at what the functions' names are. So from that, from the presentation here, we had some commands. Info functions is the first one I always run on GDB. Info functions. This is going to print out all the functions that it knows of right now. So we can see here, and it's looking pretty similar to what we saw last time. There's a lot of system ones. Some ones of interests are printf, so that's probably how we're outputting data. And then the other ones that look interesting here, if we ignore all the ones that start with underscores and any of the ones that look too complicated for what David would have made in a minute, we have two functions, main and checker. So all we need to do for that, if we wanted to go into those functions and look at it, break main. So break, we'll set a breakpoint in the program's execution, and then at whatever place you want it to, which we can use the alias main for that. And you can see here it sets a breakpoint, and then we'll also break at checker. So that set 2 breakpoints in this executable, which means when we start executing it, the second the GDB recognizes it's in one of those functions. It will halt all execution, give you control again, and you can start analyzing the program by hand. So now we just need to type run, and that'll actually run the executable. And we can see it's starting the program less simple, and we've hit our first breakpoint. So we're officially in main. The point of having this breakpoint and not just stopping right at the beginning is there's actually a lot of instructions that run setting up the program for execution. So it's not as simple as, oh, well, the first instruction executed would be the first one of main. There's actually a ton of header data and setup and stack building and all this stuff. So breaking at main, and we're good. So now we can use another one of my favorite functions, disassemble, or I think you can actually shorten it to disas. Okay, so if we disassemble this, we can see this is the raw instruction list again. So these are all those hex values I said that you could by hand convert into binary and then break them up and all that stuff. This is just going to show you the CPU instructions. And when you look at this, or when I look at this, I have no clue what this is doing. I've been doing this for a while now, and I did it partially over the summer of my internship, and it doesn't get, I mean, it gets easier, but it doesn't get like, I don't know anybody that could read this and be like, oh yeah, that's clearly a for loop, or like whatever. And if they say that, I'm gonna call them on that because I think they're lying. So either way, there's a ton of information here. And the most important part of reverse engineering is being able to know what information you can ignore. Like when I listed those functions, there's a lot of information there that we just don't need. So you just need to be able to pick up on the things that are unimportant. We're ignoring, I don't know, any subs or moves or anything. I generally start by looking at call functions. So those call instructions are pretty good indicators that there's a function being called. So we can see the first thing is call printf, which is probably printing that prompt that it gave us to input data. So it prints out that prompt, some stuff, some stuff, some stuff, some stuff, and then it calls scanf. So there's where we're getting prompted input again. So if we were to break after that call function, we would get prompted for inputting our guess again, which is awesome. Some stuff, some stuff, some stuff, and then we get to another call on that checker function. So that's a pretty good indicator that we are in the right area. So there's reading in user input, and then there's a checker function, which I imagine is going to take our guess, our entered guess, and compare it to the actual answer. So we can exit that. We've got a pretty good understanding of what we want to do, and we already set the breakpoint at that checker function. So if we just hit C or continue, and it will start the execution back up again after the breakpoint's been entered. Hit continue, and now we see that prompt. So we're passing the scanf call, and it's asking for a password. David, you know what, we'll do I spare. Okay, cool. Enter, and boom, we hit our second breakpoint, which makes sense. If we look at the instructions, we had that call to scanf. After that, a couple instructions ran, and we jumped into checker. So it makes sense that right after entering our guess, we hit our next breakpoint. We're going back to disassemble because we're in a new function now, so we need to look at new data. And here's what checker looks like. It's a little bit more complicated. There's more stuff and less meaningful call functions. So in here, what I'm always looking for, specifically in instances where it's checking, like a more real world example that isn't just a CTF, is there are programs that will check for license keys. And if you have valid license keys, and if those aren't handled properly, you might be able to disassemble them and find a hard-coded license key you can use, or some hard-coded credentials or something like that. So if we're looking at figuring out if two things are equal, the CPU's got a beautiful instruction called compare, CMP. And if we look through here, there's only one call to compare. And it's here at plus 67 from where we're at currently. There's compare, and it's AL and DL, which again, those are shorthands for CPU registers. Specifically, they're the lower half of the RAX and RDX registers, which is kind of unimportant. But either way, we found this memory address. So what we can do now is we're inside of a function. We want to set another breakpoint. So I'm going to copy the memory address. This is the actual address in the running process's memory where these instructions reside. If we take this memory address, we copy it, and then we do break a star, because it's a pointer like in C, and we point it to that memory address and hit enter, we've set a third breakpoint. And this breakpoint will be at that compare. So now we don't even have to care what all these other instructions are doing. Just ignore all of that and jump to the part where it's doing a comparison. So we can continue from here, and we're back at our next breakpoint, which is at these two memory addresses are the same minus some padding. So we're at the next breakpoint. We can go ahead and disassemble again to get a better look. So now we're comparing, if we step over this process, if we step into the next instruction, the CPU will compare the AL information to the DL information. So now comes the question of, well, what information is stored in those registers? We can get that by looking at info registers. So the same way we did info functions and prints all the functions, info registers will print all the information of the CPU registers. So here's what a CPU looks like while it's executing, or at least the registers in a CPU could look like while they're executing. This is all very platform specific. These names, these are the names of the registers here. This is the hex value, and then this is the decimal value of what's being stored there most of the time. So the RA register, like I said, this comparison is looking at AL and DL, which are shorthand for the values in RAX and RDX. So if we look at RAX here, it's got hex 69, nice, and decimal 105. And then RDX has hex 47 and decimal 71. And at first it's like, okay, that's not super helpful because we're looking for a string, right? And those aren't necessarily strings. But if we come over and we do hex to ASCII, so the way strings are stored in a computer isn't in any sort of meaningful format. It's usually in hex or binary, but we can represent it in hex. So if we do hex 69, we can see that's corresponding to the value of I, which, if we remember back to the input I fed into this program, was ILspy. So that's probably the first character of that string that I passed in, which must mean that this other register, our DX47, would be the first value of the key that we're comparing to. And we can see it's a capital G. So sweet, we're on a roll. And what we can do from here is, since we already have a breakpoint here, we can just hit continue again. Oh shoot, I thought you could. Okay. So the way that this is probably working is it's comparing each individual character one by one through it. So if we were to rerun this program, and we step through and we enter ILspy again, and we step through, okay, so we're back at our comparison now, the compare to AL and DL, and we're looking at the first values. We can actually do x/s and $RBP. Yeah, okay, so what x/s does, that was the last meaningful instruction that I put here. x/x can be examine. The first x is for examine, slash, and then the format you want to display it in. So in this case, we're going to display 15 strings, essentially. The S is for strings. You can also do X, and it will display 15 bytes in hex for that. But when you're looking for strings in a binary specifically, this is the most useful one. So here we can see that there is ILspy. My guess is being stored on the memory address here. So you could manually go around and poke around at here and see if you can find where the other value is being stored. I'm not sure off the top of my head where it actually is. But either way, we have a pretty good idea of how it's working, and it's so it's comparing those bytes, and here's where we can probably go back and you can repeat that process and go through this loop a number of times to figure out where each character is, because it's taking the first character and then it'll go to the second. So you could manually go through and dump out all those characters by hand. Or, since this is first and foremost kind of a Ghidra demo, I'll show you what it looks like in Ghidra. So we're going to do the same sort of stuff. Analysis, yes. It'll run through it super, super duper fast. We look at the functions, and boom, here's our main function. We can see, very simple here. I'll rename a couple variables. So this would be our entered guess again. This is going to be like a isCorrect value. So now we can see that we pass in our entered guess into this checker function, and then the results of that isCorrect are checked. If isCorrect is 0, then we print out, oh, too bad, you suck at hacking. Otherwise, we say, awesome, you did it. So from here, the way Ghidra works is really awesome, because you can just double click on this checker function, and boom, we jump into this checker function. And here you can see, okay, this is interesting actually. Yeah, okay, so it optimized this loop a bunch, because I had a really gross loop written here to check each individual character. But we can see here, so this value is probably a counter, or yeah, this is a counter, so we can rename this variable to counter. And here we can see it's going through each step. Param1, we already named that in the outside part. We know that that's the guess. And we can see here that the counter So this is how you access the individual characters of a string if it's an array, is we do 0, 1, 2, and go through here. And that's where it was getting this capital G from. And then our guess, ISpy, will also do the same thing, and we get that I. So there's sort of two approaches to attacking this. You can make this impossible to do in Ghidra by doing more aggressive compiling. So you strip out a lot more symbols, you make it so it doesn't have any function names, and it's really hard for Ghidra to get a grasp on it. And in those cases, you're going to want to fall back to using something like GDB to manually go through and check it. Yeah?
Is there an advantage of using GDB over Ghidra?
Yeah, so there's a lot of cases where, like I said, if you compile, I just did these with the basic GCC compile command. If you do GCC with some specific commands, you can get it to strip out all of the information about how many header or how many functions there are, where they're located, a lot of metadata that Ghidra uses to put together this really awesome snapshot of the program. And if you have a binary that's compiled and you throw it in Ghidra and it can't find any functions, it's probably because all that information's been stripped out manually. So in those instances when there's no metadata to go off of and Ghidra can't get a decompile, that's where I switch over to using dynamic analysis. Because then you know you can at least like, when you do dynamic analysis, no matter how much information there is, you know that the information you're looking for is there because it's literally what's running on the CPU. So that's what I usually end up using it. But it's also it's slower and it requires a lot more effort and usually a lot of restarting. So yeah.
So how does that X thing work again where you?
This X, yeah, X/X RD RAX. So it will examine the memory at the location you pass in here, which is a register at this point. And then this second X is the format. So you have X for hex, you can do D for decimal, you can do S for string, P for pointer if it wants to jump to a different place, a whole bunch of stuff. So it's like the easiest way to just dump memory at a certain place. Because there are a lot of times when these registers will be at, like these registers here, these aren't normal values, those are memory addresses. And so if you wanted to look at the memory at that address, you could do X/P RBP, and then that will look at, X.S. And so that will dump the memory at this new location following the actual redirect. So yeah, there's a lot of really complicated GDB commands that I haven't ever used, but they're, it's probably the most powerful debugger dynamic analysis tool that I've ever used. But it does require a lot of learning, a lot more learning than Ghidra does, where you can just, like I said, drag and drop pretty much. So cool. And then finally, I just wanted to show off that Ghidra doesn't always work. So talking a little bit about, we were mentioning that there are some instances where Ghidra's not going to be great. So I have this other demo here that's been compiled into a release format and here, and then we'll do the Windows one, because why not? So this is a compiled program. It's a .NET program. It's written in C#, and there's a million files with it because .NET's like that when you compile it. So this is pretty crazy. And these are all like crazy system things usually that we don't care about. There are tons of files associated with this very small program. But we can see in here, there's a couple interesting ones. So we have, I doubt anybody can read that, but that's demo2.exe. So that's the actual executable that you run when you generate this Windows program. And there's also PDB, I don't remember what extension that is. Anybody know PDB? Portable, something, I don't know. And then there's the DLL, which is a dynamic link library, which is usually imported into other functions to make it reusable code. So obviously, if I wanted to figure out, oh shoot, I should probably run this actually. We're gonna exit GDB for a sec, or quit actually. Yes, clear, okay, cool. What? Portable database? Program database file. I don't know what a PDB file does. Okay, so cool. In here we can do .NET run. And we are going to run this C# program. Oh my God, guess what? It's another password guessing thing. Sweet. Testing. Oh, this one's fancy. It's got a loading bar. Oh, that ain't it. So this one's a little bit weirder. But again, we can just go through and try to do this in Ghidra. So demo2.exe is what I'm running. Probably the information's in there. I'll throw it in Ghidra and see what it does. You can see here, it identified it as Windows, x86 still, and it's an exe file. No problem, Ghidra handles exes the same way it does ELF files and all sorts of stuff. Of course you want to analyze this. What worth is it if I don't analyze it? Why would you even give me that option, Ghidra? Cool. Analysis C in the bottom right, it's taking a bit longer because this is a larger file and it's an exe, and it's kind of stupid. So it's going to go through a number of different steps to analyze everything. With these sort of window files, it also imports a lot of system libraries that it needs. So these exes usually don't have a ton of information themselves. And you can see here, these functions aren't super interesting. I don't, like looking at this, if I didn't know anything about this function, I would not know where to start. These don't look like, there's no main function, which is what I usually look for. There isn't really any function that even looks like it's super interesting. I just don't, I don't know. We can click through these and look for new things. Sometimes there's hidden in other folders, but the best I do is entry, which I know is where you enter the actual program. But even this looks like garbage. Like I don't know what any of this is. So it's programs like this where I start to get pretty lost inside of Ghidra. So those other examples were really easy for Ghidra because they were really short C programs. But even that decompiled code over there doesn't look helpful. I mean, there's a bunch of unknown things. There's a bunch of crazy function calls. So if you ever find yourself in a binary like this, one of Ghidra's strong suits is searching for strings. So we know guess my password has to be in this program somewhere. So let's go ahead here and we can do tools or search here and search for strings. And here we can set the minimum, maximum length, alignment, whether we require null terminators, and we can just search. And this is essentially doing what the strings command does, but inside of Ghidra, and it will jump you to the memory address where things are. So in this view here, we have all the strings that it identified. We can scroll through, and I'm still not seeing anything super useful. And there's a ton of them. So we can actually filter and just try to look things up. So what was it we were looking for? We're looking for guess my password. So we'll just do guess, and it's not there. That string just doesn't exist, which means that it's not printing it out because it has to exist in this program somewhere if we're going to be printing it out. So it's at this point that I start to think, okay, maybe what we're looking for isn't in the demo2.exe file. So let's go back to Ghidra. We're going to open up a new file. We'll close this out, and we'll import a new file. So back to import. And demo2.dll is usually a good guess. When you're dealing with EXEs, they have to import a lot of files. For anybody that doesn't know what a DLL is, it's like a shared library. It's a dynamically linked library. So if you have a bunch of code that's going to be reused across a ton of programs, just put all that code in DLL, have those programs import the DLL, and then the next time you need to update your code or anything, you only change it in one spot. So let's look at demo2.dll, because Ghidra will handle DLLs pretty well as well. So, well. Let's open up that DLL. And we'll give it its best guess at analyzing it again. DLLs are a little weirder because they don't have the same, like, here's the main function, and that will run code. It's usually a bunch of disconnected functions that, when they're imported, get called by a main function. So a DLL doesn't have a main function in itself, so it's a little weirder to get a grasp on. And we'll look at the functions here. And as I'm a liar, it has a main function. But the main function in this case is garbage. So it's named main, but if anybody can make sense of that decompiled garbage, I'd be surprised, because I have no clue what's going on here. There's like half compiled instructions. There's a ton of weird calls to things and a lot of registers. So again, feeling pretty bogged down. This one's only got 3 functions, and they're all really weird and gross. So this seems like it might not be it either. But I always like to go through and look for strings. So strings, we'll search for them. And, oh, okay, so it actually is pretty interesting. So we have this text here, which is the actual string for the executable. It's going into that project, so we didn't see that in the other one, which is nice. And we can scroll around, but if we do guess, hey, okay, sweet. So it actually does have the string stored in memory. So apparently those constants that were put into that program are being stored in this DLL and then imported. And these are all artifacts of the compilation process for .NET programs. So, okay, cool. If we look at that in code, so when we click on these, you can see the background is jumping around. Ghidra will actually jump to the, okay, no, it's not. Ghidra will actually jump to the memory address of the string you're clicking on. So, yeah, we can see here that guess my password is right here. So if we do that, we can see guess my password. This string is stored here in memory. Checking, which was printed out after that. So we had this checking function. And then there's a string here, which looks like you're getting better at this. So that's probably the answer to the correct version of it. And then here's the wrong answer. And then down here a little bit below in memory, we can see hacking for profit with some leet speak in there. So anytime you find one of these strings buried in one of these executables or a DLL, probably a good chance to throw that in and see what happens. So we can do .NET run again, and we can give it hacking for profit. checking, and boom, you're getting better at this. So that was a slightly different example. So when you're dealing with EXEs and they're broken up to a bunch of stuff, don't get discouraged if you can't read the code as clearly as Ghidra does on those first examples. It's very rare to find EXEs in the wild that are going to decompile that perfectly. And it only did that because I put in no effort to strip any of the symbols or to obfuscate any of the code. So in more complex examples, it might take, you might not really understand what the code's doing. This decompile might not help you that much, but you can still gather information by just poking around with strings, searching the memory for specific hex combinations of characters. And through enough brute force and trial and error, you'll probably be able to find what you're looking for because in the end, I mean, it's just a computer. And that computer has to operate on some data. And if you can find that data, you're golden. So that is pretty much it for the presentation. We're actually like perfectly at time, so that's cool. But yeah, I hope everybody can go and download Ghidra. I think, are there any binaries on the IASG website for like little poke around challenges?
The answer is probably, but no one solved them, so no one actually knows what the correct answer is.
Yeah, so I think we might have some binaries hosted on the IASG's website still that would be useful for throwing in here if you wanted to play around with it. But again, Ghidra's open source, free. I'd recommend everybody download. Oh, we don't have any on the IASG website?
We can put some in Discord.
We could put some, we could throw some stuff on there. I would really recommend everybody to go download it. And worst case scenario, you get to practice your C programming and then also practice your reverse engineering. So make a program for yourself and play with this by yourself. Yeah.
How big is the download for Ghidra?
A couple hundred megs.
It's pretty small.
Oh, it's pretty small.
Yeah.
This is great work. It's like basically
It's Java. It runs everywhere.
Thank you everybody for coming and hanging out. Oh my god, thank you guys. You guys shouldn't have. You shouldn't have. Yeah, the whole download's pretty small.
Yeah, I want to say it was like,
imagine not just like Android.
All those files are pretty tiny.
Actually,